Okay, here's our second video on comparison tests. In the first video, we dealt with the direct comparison test. In the second one, we're going to be dealing with limit comparison test. Sometimes it's just advantageous to compare them this way, and this one is obviously, you're still comparing the given series to a series that is similar to it that you sort of conjured out of your mind, hence why these are paired together. Basically, you're given a sub n. Suppose that sigma of a sub n and sigma of b sub n are series with positive terms. If the limit of their ratio is equal to c, and c is a finite number that is greater than 0, then either both series converge or both series diverge. So here's how it plays out, okay? Let's say that we're given, let's go ahead and undo the zoom. All right. Now, let's say that we're given sigma n is equal to 1 to infinity of 2 to the n plus 1, 5 to the n plus 1. Well, that looks awfully similar to 2 to the n over 5 to the n, or, what's more commonly written as 2/5 to the n. So what I need to do is I need to place these in a ratio and take the limit as n approaches infinity. So the limit as n approaches infinity, and it doesn't really matter which one goes on top and which one goes on bottom, because here's the thing. If it's 1/3 one way, you're just going to get 3 over 1 the other way, okay? It's not a matter of what the integer is, or what the value is. It's the fact that the value is finite and greater than 0. So let's go ahead and let's just put 2 to the n plus 1 over 5 to the n plus 1 over 2 to the n 5 to the n. Well, I don't really like the complex nature of that fraction, so we're going to go 2 to the n plus 1, 5 to the n plus 1 times 5 to the n over 2 to the n, right? To divide by fractions, to multiply by its reciprocal. So we wind up with 10 to the n plus 5 to the n over 10 to the n plus 2 to the n. And you could use your infinite series sort of stuff going on here, but you need to remember that 10 to the n and 10 to the n are going to increase so much faster, okay? And actually, let's go ahead and do it. 1 over 10 to the n and 1 over 10 to the n. You can wind up with 1 plus 1/2 to the n over 1 plus 1/5 to the n. And as n goes to infinity, both of these values go out, and I get 1. Now, is 1 greater than 0? Yes, it is. And therefore, since I know that this is a convergent geometric series, and the limit of the ratio of, this one we'll call a sub n, and this one we'll call b sub n. I put them in a ratio, I ran n off to infinity, and the limit wound up giving me a finite positive number, and therefore both are either convergent or both are divergent. This is convergent, therefore this one must be as well, okay? And that's basically, limit comparison winds up being a little bit trickier and a little bit more involved than direct comparison, but not much. You still have to use your hunches in order to find the thing that you're looking for, like find the actual function that you're interested in comparing it to. Actually, I don't really need to put the number. These aren't out of your book. Let's do sigma n is equal to 1 to infinity of 1 over n squared n plus 3. Well, I know that that is somewhat similar to 1 over n cubed. So let's go ahead and take the limit of their ratios, 1 over n cubed plus 3n squared over 1 over n cubed. When I simplify that complex fraction, it winds up being n cubed over n cubed plus 3n squared. I can do that in a more robust fashion by multiplying by 1 over n cubed over 1 over n cubed, or I can just recognize sort of algebra 2 pre-cal style. I just need to compare the leading coefficients. This is synonymous with an end behavior asymptote kind of question for a rational function. It's 1. That is greater than 0. It is a finite positive limit that you have arrived at. Therefore, both are convergent or both are divergent. Well, this is convergent right here. It's a convergent p-series. So both are convergent by the limit comparison test. Alrighty, let's keep going. So we have n is equal to 1 over infinity of n over n squared plus 1. Now, that's a little bit trickier, but I happen to know that if that plus 1 disappeared, I'd have 1 over n, because it would reduce. So let's compare it to 1 over n. This, we happen to know, is a divergent p-series. Okay, so if this winds up giving me a positive integer for the limit, then they are both divergent. Okay, so let's do the limit as n approaches infinity of n over n squared plus 1 over 1 over n. When I resolve the complex nature of that fraction, I get n squared over n squared plus 1. That is indeed 1. They are both divergent. Now, notice that I could have also done this one by the integral test, because that is related to that. And I could have done it as the integral of 1 to infinity of x over x squared plus 1 dx. And of course that would have been 2 and 1/2. And then I would have had 1/2 limit as b goes to infinity of 1 to b of 2x dx over x squared plus 1. 1/2 limit as b goes to infinity of the natural log of x squared plus 1 from 1 to b. If I have 1/2 the limit as b goes to infinity of the natural log of b squared plus 1 minus the natural log of 2, I recognize that by the integral test, this also is divergent because this term right here goes to infinity. So notice, again, this is one of those ones that could have been done more than one way, okay, by limit comparison, but also by the integral test, okay? So be aware of that as we move forward. Oftentimes there's not one singular way to do it. There's multiple ways to do it. Okay, how about n is equal to 1 to infinity of 1 over n square root of n squared plus 1. Well, and the thing is that what happens is you just need the instinct comes from just trying to ignore the plus 1s and stuff like that. Because if you don't have that plus 1 and you're just dealing with positive integers, that winds up being that. Okay? Or, you can actually, and because you can compare it to that, right? For positive integers, those are exactly the same thing. And therefore, I know that the limit as n approaches infinity of 1 over n times the square root of n squared plus 1 over 1 over n times the square root of n squared. When I resolve the complex nature of that fraction, I get n square root of n squared, n square root of n squared plus 1. Those cancel out, of course, and I'm left with the limit as n approaches infinity of the square root of n squared plus 1, and there are, a dozen different ways to actually resolve that, but you notice that that's actually going to wind up being 1. It's a positive finite value. Therefore, they're either both convergent or both divergent. This is a convergent p-series, and therefore you just write out because, because sigma is equal to 1 to infinity, 1 is a convergent p-series, and the limit, sigma n is equal to 1 to infinity of 1 over n squared plus 1 is convergent by, and then you just put limit comparison test. Sorry, my handwriting today is horrible, but you guys are used to it. Okay. And you would just state why it's convergent. You would state why the original one is convergent, and then tell what test you used, and tell the conclusion that you come to as a result. Okay. Well, let's go ahead and let's do how about 5 to the n plus 1? Okay. Well, this should look awfully similar to that. Now you can do it by direct comparison. Can you do it by limit comparison? All right, let's go ahead and check. Limit as n goes to infinity of 1 over 5 to the n plus 1 over 1 over 5 to the n. When I resolve the complex fraction, I get 5 to the n over 5 to the n plus 1. And you can do your more robust version of finding infinite limits by dividing or by multiplying through by 5 to the negative n. But that limit is 1. It is a positive finite value. If it is a positive finite value, then this, being convergent, tells me that this is also convergent. It was also by direct comparison. If this is convergent, this for every n value is smaller because it has a larger denominator. So you could have done that also by direct comparison. Now we've done several examples of direct comparison and limit comparison. I hope that that actually sort of gives you an idea of kind of what we're doing in terms of this. Email me with any questions, clarification, and stuff like that. I think this is a good sort of intro into the comparison test. We'll go ahead and start up in the next video with the alternating series test. So look forward to that. Bye.